A Guide to EAA. Welcome to Part 1. What is EAA? In Part 1, we're going to cover what is EAA. We'll give you a brief history of electronically assisted astronomy as well as video astronomy. We'll talk about why you may want to do EAA. We'll set some expectations, and then I'll go through a few of my own examples. So what is EAA? So is EAA imaging or observing? On the one hand, we have visual observing, which is basically your typical look through the eyepiece through the telescope, and then you have your imaging or astrophotography, where your camera is actually taking exposures and you're gathering data and ultimately coming up with a beautiful picture. Well, EAA is kind of both and neither. It falls right in between. EAA shares many similarities with both. So what is EAA? And you're going to find a lot of definitions out there, but here's what I think. It's something that was born out of video astronomy, which is where people would put a video camera up to the eyepiece. It's about observing an object in real time, or as close to as possible as real time, and not necessarily collecting data for later processing. So instead of using an eyepiece, you're going to use the sensitivity of a camera to enhance your view of the object. Again, the emphasis of now and not necessarily later. And it's also about exploiting the technology either inside of a camera, a night vision device, or a computer to enhance the view of that object, again, now and not necessarily later. Most purists are going to agree and say that if you're going to do some sort of post-processing, it's not EAA, rather it's imaging. And if you go on cloudy nights, this is an ever-evolving subject. Let's further break down EAA, and we can think of one category as our night vision devices. So this is where you're using some sort of night vision technology to replace the standard eyepiece. These have some amazing sensitivity, and you're looking at basically these images that are live and not processed or stacked or anything, that is absolutely real time. However, these can get incredibly expensive, more expensive than your telescope and eyepieces and typical astro cameras combined, several $1,000s for each individual night vision eyepiece. Next is when we take the camera and we replace the eyepiece with our camera. So we can use a DSLR camera, an astronomy camera, you can use a smart telescope, or you can kind of go real old school and use a security camera or video camera. And when you actually remove the eyepiece and use the camera in its place, that's called prime focus. Now, any of these cameras can be used in video mode, or more popular now is basically taking longer exposures that are stacked together. And I'd say this is the most popular form of electronic assistance when we talk about EAA. And then we talk about a camera over the eyepiece. So here's where we're going to take your telescope and your eyepiece and then connect that camera to the eyepiece. This is also called a focal projection. And you can pretty much use any camera, especially smartphones. And you're going to need some sort of adapter or threaded connections. I will give a bit of a warning that some of the adapters can be very, very fickle. Sometimes it's very hard to get the right placement of that camera lens over the exact right spot of your eyepiece. I highly recommend ones that will allow you to do micro adjustments in kind of all three axes, so both the kind of the X and Y axis as well as the Z, so basically going basically up and down over the eyepiece. The Celestron NextYZ, which is the device that's pictured on the left, is one of those devices. So that's a breakdown of EAA in terms of the different devices, or how we can split that apart. A brief history of EAA. Now, the earliest reference that I can find about some sort of EAA or electronically assisted astronomy or video astronomy was actually this 1928 article by Donald Menzel of the Lick Observatory out in California. And he published this article about the emerging technology of television to broadcast views from a telescope. See the observatory with its battery of telescopes, which will transmit the television images. These images will then be explained by radio messages sent out from the observatory. At the receiving station with a color projector, it's able to throw an image up onto the screen. So the article goes on to say, some time ago it was remarked that the extreme sensitivity and amplifying powers of a vacuum tube would find an application in astronomy. With the advent of practical television looming not so far in the distance, this possibility is rapidly increasing. And that television will make it more possible to receive an image upon the sensitive cell of a sending apparatus and magnify them greatly upon reception, this permitting a more comfortable, detailed study of the object. It is even possible that a battery of telescopes trained on the same body may be utilized if red, yellow, and blue filters, respectively, be placed in front of the image in 3 telescopes. It would form colored views of the planets or stars under consideration. Then these separate images could be combined into one receiving set. So incredible how they were already thinking about some of these astrophotography techniques that we use today. And then we have this really interesting picture of this gentleman, Gil Miles, of the Sydney Amateur Astronomers. And he is using a video camera with his, what I believe to be some sort of Newtonian, maybe. And he's got that camera connected to what I would barely call a very portable television set. But you can see here, it looks like he's viewing the moon. And what I find even more striking is his outfit. He's definitely dressed in a or what we would consider very well dressed or dressed up for such an event. So in the mid-90s, amateurs began experimenting with some very inexpensive CCTV security surveillance cameras, and one such example was this Super Circuits PC23C. And these were okay for bright solar system objects. And of course, these were just black and white. But then in the late 90s, you had companies like Stellacam and Malincam, and they came out with some very sensitive cameras, but the cameras had some very, very small chips, which resulted in a very narrow field of view. But innovations kept coming. In the 2000s, we started seeing some color cameras and the ability to cool the chips, allowing for longer exposures. Then we had users also experimenting with security surveillance cameras such as the L300 and various Samsung models, which were a huge improvement over the previous Super Circuit models. And then in the 2010s, we started getting larger chips, dedicated astronomy cameras with their lower read noise and the ability to control the entire camera with just a single USB cable. In the late 2010s and the early 2020s, the software really came into its own, allowing for longer exposures, the ability to do all sorts of real-time enhancements, the ability to improve the tracking, and also making sure that you've got alignment of frames, and the sensitivity and intelligence to be able to now align and live stack the sun, the moon, and the planets. And now in the mid-2020s, we've got smart scopes. They've exploded onto the scene, providing some amazing results with very, very little effort. And thanks to its automation and frankly, very inexpensive price tag, these are incredibly beginner friendly. So why do EAA? Well, one reason you may want to do EAA is to increase your light grasp. So I'm going to show you this sketch of the nebula M57, and this is from a Bortle 3 sky out in West Virginia, and it's captured through a 14-inch SCT. Now, I'm also going to show you a screen grab. This is a 20-second capture from my first video astronomy camera, and this was from Bortle 5 skies, so definitely some brighter skies, and it's from a smaller telescope, an 11-inch SCT. Now, when I take a look at the sketch and what the observer, the dimmest object the observer was able to see was this star with a magnitude of 15.3. Now, when I look at the image I took, the dimmest star that I can see in this image is this star at 18.45. Now, when you actually compare the two, that is actually a difference in brightness of 18.2 times. So in other words, the star that I'm able to see through this EAA screenshot is actually 18 times dimmer than the dimmest object that this individual was able to see when he looked with an eyepiece and his larger telescope. Now, another reason to do EAA is to overcome light pollution. And this is a great example. Again, we're still looking at M57, but this screen grab was taken from Greater London in Zone 4. So that's basically Bortle 8-9. And it's 100 seconds from a 12-inch SCT. And you can clearly see that not only are we seeing some good detail, but we've got some great color coming from a very, very, very light polluted location. Another reason to do EAA is that it makes a phenomenal outreach tool. So I've got a couple of examples here. The one kind of center at the top, we've got a globular cluster being projected on a TV, or actually a computer monitor for folks to come and look at. And in some of these other scenarios, we actually have the object that we're looking at being projected onto the ground. For lots of people to partake. So it's a great way for folks to be able to see an object and be able to interact with you instead of these big, huge, long lines that might be forming behind the eyepiece, and you never really know if the person looking through the eyepiece is actually seeing something. Did they get their eye in the right spot? Is it focused for them? So this sort of EAA is a great complement to your traditional types of outreach. Now, here are a few other reasons why you might want to do EAA. And first, it allows the enjoyment of astronomy for those that have potential accessibility issues or eye conditions. So obviously, someone trying to, in a wheelchair, trying to get up to your scope and look through an eyepiece is going to be very difficult. Or if somebody has some sort of difficulty focusing or issues with their eyes, they're going to be able to see a projector, something from a projector or a TV monitor screen a whole lot easier. Young children also have a difficult time looking through an eyepiece. If you've ever seen at an outreach event someone trying to hold their kid and then trying the juggling of trying to get the kid to put his eye or her eye over the eyepiece, it's at times quite comical, and you never know if they're going to see anything. You can also enjoy images in color rather than shades of gray. The great example was a few slides previously showing M57 in London, or from London, in color. It also allows for internet broadcasts and virtual star parties. It's also very amenable to remote control and viewing. I personally set up my scope outside of my garage, and when it's cold outside, I can actually be inside my den and controlling the telescope and doing all my viewing from the comfort of my home. And it's also capturing photons much more effectively than the human eye. So you basically are increasing your light grasp with a smaller aperture scope. In other words, you don't need to continue to buy larger and larger aperture telescopes to get some of those dimmer objects. And it allows for viewing dozens of objects in a single evening versus, let's say, traditional astrophotography, where you might be lucky to get 2 or 3. And given that we're now post-COVID, but should anything like that ever happen again, it is a nice form of socially distant astronomy. So why would you maybe not want to do EAA? Well, depending upon your setup, it can actually be rather difficult to operate and take down. So you've got more cables, you've got to deal with monitors, you've got extra equipment, and you've got to bring some sort of power, especially if you're remote. And the use of projectors and monitors and laptops may actually increase stray light. So you don't want to be that astronomer that is lighting up the whole field with white light from computer monitors and ruining everyone's dark adapted eyes. So make sure you practice good astro neighbor behavior. And of course, more can go wrong than with viewing an eyepiece. And obviously, there's you never know, does you blow a fuse or your alignment's not working or whatever. It can really ruin your evening, and you don't do any observing trying to track down any potential problems or any issues that you might have. And there's also a steep learning curve, especially for some of the software. The software is amazing. It can do amazing things, but it's going to take time for you to learn and get acclimated to the actual process. So several nights of experimentation are definitely recommended, and it's going to take you quite a few nights to get up to speed. Let's set some realistic expectations. So we've mentioned that EAA is going to increase the light grasp of your telescope by quite a few factors. And that is fantastic on dim objects like galaxies and nebula and globular clusters. But you're not going to get that same sort of shimmer out of open clusters. And you lose a little bit of that emotional tie when you're looking at something on a computer screen versus actually looking at it through an eyepiece. And regardless, it cannot compete with the dynamic range of the human eye. If you want to see planets as well as the moons of Jupiter going around it, you're going to have to do quite a bit in with computer software to be able to allow that to happen versus just looking through an eyepiece and a telescope. You're going to be able to see that. So again, EAA, you're not going to be able to compete with the dynamic range of the human eye. And you're not going to get photographic quality for tens of seconds to maybe a few minutes of doing EAA compared to hours and hours of data gathering and processing. So, for example, this is one of my snapshots of the M51, the Whirlpool Galaxy. This is with my very first camera and 20 seconds of exposure. I had this is an upgrade of one of my current cameras. This is about 5 minutes of exposure. Very, very happy with this picture. Again, it's absolutely amazing, the detail you can see, but it's still 5 minutes of exposure. Now, when you take a look at, let's say, again, with another same C11, this is 75 minutes of exposure plus a lot of post-processing. So again, don't expect photographic results, but again, what you can see compared to, let's say, the visual view of just a fuzzy blob where you can barely make out the arms of the galaxy compared to what you can do with EAA is amazing, but just don't expect photographic level quality. So here are a few of my own examples. This first set of examples comes from my very first video astronomy camera. It was the Astro Video Systems Mark IV, and this was a standard resolution CCD camera. So the actual number of pixels in each image were 600 and I think 20 by 480. So again, not necessarily anything large that's going to fill up a computer screen, and they were a bit blocky. The camera was very sensitive, but it also had a fair amount of noise coming through, and also with the going from the basically the analog out of the camera and then converting that signal back into digital to be captured in the computer, that also caused some weird artifacts, and occasionally I'd get these kind of pixels that would blink on and off in different colors. But we have some examples of the Eagle Nebula, the Crab Nebula, and so forth. So definitely more detail than you can see with your eye, but certainly not photographic. I then upgraded to a entry-level astronomy camera, and this was the ZWO ASI 385 MC, and it was a cooled camera. And it did a pretty good job, but it was lacking in some of the ability to basically get a depth of different colors. But it was still a huge improvement over the previous camera. But I did find myself wanting a little bit more in terms of improved optical quality. So I'm now using something called an ASI 533 MC Pro. This is also a cooled camera, and I'm very happy with the results. Obviously, I think this is a huge improvement in as compared to the previous cameras. So we've got the Orion Nebula, another Eagle, or shot of the Eagle, and so forth. And I'm also very impressed with, and the software is also improved. So now we're able to get some amazing pictures of planets. And although it's a different telescope and a different camera, but I did want to show an example of the sun using a monochrome camera, an H-alpha telescope, and sharp cap with artificial coloring of the sun. So thanks for watching, and would love it if you gave this video a thumbs up, and feel free to drop a comment. And stay tuned for part 2.